and then I find a way to get caught up.
Okay, so to review real quick, we talked last time about, where is it? There you are. About our definition of what it meant to be a radian and the idea of looking at a different measuring system. Work with me. There you go. And the idea of 1 radian being the amount of arc necessary to make this inscribed length the same as the radius. And that was what we ended up with for 1 radian, right?
Mm-hmm.
And the nice part about that definition is when we kind of expanded it to some random number of radians, that radian measure, theta, for some arc S, the ratio between whatever that arc length is in ratio to that radial length is our definition of that angle theta. Essentially, whatever that radial length is, say it's 13, not the radial length, sorry, whatever that arc length is, call it 13. And if that radial length is, say, oh, I don't know, 10, then this angle is defined by that ratio between how much arc length is produced in a circle of what radius. Right?
Is it really that simple?
Yeah.
It didn't feel like that on the homework.
Well, one of the consequences of that, because our angle is defined in terms of relationship between an arc length and a radius, arc length and radius kind of naturally have an irrational relationship. And we talked last time about the full rotation being taking about 6 of those to do it. So it's about turned into exactly 2 pi radians to go all the way around, right?
Mm-hmm.
That means whatever that, that circumference is, if you take that circumference and divide it by that radius, that circumference divided by radius is always going to be 2 pi, because that's, the definition for our circumference. Divide that by that radius always cancels out. But that radian measure of a full rotation is an irrational number, but it's a fairly clean one, being just twice pi. And from that, we built the rest of what we thought of or are going to be thinking of as our standard angles. And I believe last time we built this circle and the standard angles in that circle, right?
I think so.
Yeah. And I encourage you guys to practice building those by counting around and breaking it up into fourths, as well as breaking it up into the sixths and the thirds. Not drawing as straight of lines as I usually like to, but that's okay. and counting those around. Now, kind of an open question last time was, well, why these angles are more important or more significant than other angles. Yes, these are nice cuts of our circle. I mean, cutting it into halfway and a quarter and an eighth, you know, those are reasonable things to do, but why is that more significant than cutting it into, say, fifths or sevenths or something else? And part of that comes into when we start to define our trig functions. So before we talk about those trig functions, was there anything particular about this? I know I tried to review that very fast, but anything about that definition of our radian measure that you guys want to ask about or talk about before we start talking about those trig functions? Why are you guys all perfectly still? Oh, there you guys moved.
I would assume that dividing up the circle into quarters and then thirds and then fourths would give you a good landmark for when you're working with uncertain numbers, where it's like, oh, somewhere in between these two numbers is the answer that I'm looking for. I feel like it would help you better pinpoint what point on the circumference you are aiming for.
While that's certainly very true, and we will use it in that way, there's actually more significance than that to these angles. And we'll talk about that today as we go along. But to see why defining those trig functions first is going to be helpful. Actually, can you guys hold on 1 second? Let me grab something. Sorry, thank you. Okay, so you guys had a chance to read over your 6 trigonometric functions?
Yes.
Just you guys? When we talk about those 6 trig functions, there are essentially 3 definitions that we're going to look at. And these 3 definitions, they all kind of nest within each other. They're all slightly different ways of looking at the same thing, the same idea. But it's going to be helpful for us to look at it in one way sometimes, and other ways other times. So when we first start looking at these trig functions, we will look at them in terms of their use in triangles. So the triangular definition is where we're going to start. So to look at the triangular definition, we certainly need a triangle, and it does need to be a right triangle. That is a restriction we will eventually break away from, but for now, we're stuck talking in right triangles. And when we have a right triangle, we've got 2 legs and the hypotenuse. So we got a hypotenuse and a couple of legs in reference to an angle, theta. One of the legs is referred to as the opposite leg, and one of them the adjacent leg. If you switch what angle you're talking about, if you're not talking about this angle theta, if you're instead talking about, say, angle phi up here, in reference to angle phi, this would be the opposite leg, and that would be the adjacent leg. Is that fair? So which one we're talking about depends on the angle of reference. Now let's give ourselves some numbers here. Let's say this opposite length had length 5, this adjacent was length 12, and the hypotenuse, let's say, was length 13. Now, one of the things that has to be true in a right triangle, as you guys are comfortable with, is that Pythagorean theorem has to be true, right?
Mm-hmm.
So we could check to see, does this make a valid right triangle? Is 5 squared plus 12 squared equal to 13 squared? Is that valid? So 25 plus 144 is 169, which is 13 squared. So that does check out. Fair? So do keep in mind that Pythagorean theorem relationship is always going to be kind of behind what we're doing. So when we have a triangle, one of the things that we care a lot about in triangles is not necessarily the particular lengths, but the ratio of lengths. The reason we care about that is because everything that's true about this triangle is going to be true regardless of its size, at least in ratio. So if each of these triangles, a little tiny one here, why not? If each of these triangles have the same angle in it, the side lengths are all different, but the ratio between those side lengths is always going to be the same. That's that concept of similar triangles. So when we talk about our trig functions, the job of the trig functions is to relate this angle with the ratio of sides that are produced. Each of the trig functions are going to take in an angle, symbol for the measure of an angle, and the output is always going to be comparable to a ratio of side lengths. Which ratio of side lengths depends on which function we're using. So, for example, the sine function, its job is to take in an angle measure and tell us what the ratio between the side opposite that angle and the hypotenuse is. So it's supposed to tell us that ratio. In this particular case, for this particular triangle, that ratio is 5 to 13. So if all of these have that same angle theta, that ratio of 5 to 13 is going to be the same ratio all the way through. This might be, say, I don't know, 5/3 and 13/3. As long as that ratio holds, those are the same sized angles.
So then would cosine be the adjacent in the hypotenuse?
It would. Well, we've got, that's one relationship, the opposite to the hypotenuse. We've got a bunch of different relationships, and you're right, the cosine function, its job is essentially the same. It's just a different ratio. The cosine function, its job is to give us the ratio between the adjacent side and the hypotenuse. In this case, that would be 12/13. Okay, well, that's these two and those two. So the opposite and hypotenuse and the adjacent hypotenuse, they have relations. The tangent function its job is to give us a different one. We've got opposite and hypotenuse. We have adjacent and hypotenuse. The tangent's job is to give us the ratio between the opposite and the adjacents themselves, which in this case would be 5/12. If you want a quick example of why we might care, let's say we want to take this same angle, theta, and we want to build a model where this length, let's say that opposite length was 110. How long would this side have to be to make it the same angle, to make it the same, essentially the same triangle, just a different scale? If this is 10, well, what side does that have to be? Well, what do we know? We know that the tangent of that angle, the ratio produced between the opposite and adjacent ratio is tangent. That ratio has to be 5/12. But the tangent also has to be the ratio between 110 and this mystery side here. Let's call it x for the sake of argument. Well, if the tangent is supposed to be both 5/12 and 110x, then the 5/12 has to equal 110 over x, and we could solve that for x. 5x equals, well, whatever 12 times 110 is. So x is equal to 12 times 110 divided by 5.
It's 264, I think. Right?
That's what I got, but I did it a different way, so now I'm doing it that way.
So it's what, 220 plus 44, so 264? That's what you said, right?
Yeah.
It's just an easy way to do it by hand without grabbing my calculator. Now here, we know what the tangent of theta is because we have this other triangle to refer to. But if we knew just this angle, we'd be able to use other tools to figure out what the tangent of that angle is and do the same problem that way. So I said there were, go ahead.
How?
We'll get to that.
Okay.
We got some building to do. So I said there were 6 trig functions. This is 3. We got 3 more to go, but we've already got the relationship between, the opposite and the hypotenuse, the adjacent to the hypotenuse, the opposite and the adjacent. It feels like we're out of combinations. And we sort of are. The other 3 trig functions, the cosecant, secant, and the cotangent, aren't so much different ratios. They're just different orientations of these ratios. So the cosecant, abbreviated CSC of theta, it takes in an angle and gives out, instead of the opposite to the hypotenuse, it gives out the ratio of the hypotenuse to the opposite. So instead of the ratio of 5/13, it's the 13/5. The secant, instead of being the adjacent to the hypotenuse, is the hypotenuse in ratio to the adjacent. Same relationship as cosine, just the reciprocal orientation. Cotangent, similarly, is the reciprocal of tangent. So those are the kind of 6 different ways we could relate those 3 sides, but half of them are really just reciprocals of what we will often refer to as our primary 3 trigonometric functions. We generally think of the sine, cosine, and tangent as our 3 primary functions. Most of what we will do will be dealing with those 3. Secant will use a fair amount. Secant comes up enough that it's going to be an important tool. Frankly, cosecant and cotangent, we don't see all that much. If you need a cosecant, you usually don't mess with cosecant. You just mess with sine and then flip it upside down. If you need cotangent, you don't play with cotangent. You find tangent and you just flip it upside down. Fair? So primarily we will care about these 3. Now you asked, how are we gonna, use this in relation just to angles? Well, there's a couple of different ways. One, frankly, if we know an angle, let's say even in degrees, let's say this is 32 degrees. And we know, let's say this is some sort of building, and we are 100 feet from that building, and we want to know if our eye line to the top is 32 degrees, how tall is that building? Just for a fairly straightforward geometric question. Well, we can find that using our trig functions. We want the opposite side here. We know the adjacent side. And our tangent function talks about opposites and adjacents. Our cotangent does as well, but tangents are primary. So we know the tangent of our angle, 32 degrees, should equal that ratio between this unknown side and that 100 feet. All we need is a tool that tells us what the tangent of 32 degrees is. Well, you have such a tool. You got a calculator with you?
Yes.
Ask your calculator what the tangent of 32 degrees is.
Uh, 0.624, etc.
So 0.264, you said?
624.
624. Anybody want to back that up or argue with that?
You could also round up to 625, but I don't think that's important.
And then that is equal to x over 100, multiply both sides by 100.
Well, first, did anybody get anything different?
No?
Nobody?
Is someone supposed to get a different answer?
Yeah.
I got 0.661.
0.661. Anybody get that? Anybody else get that?
Because he's got his calculator in radians.
Usually that's why. And that's why I wanted to look. We got to be careful because we'll get different answers depending on whether your calculator thinks that's a radian measure or a degree measure. And this measure is a little bit dangerous because those numbers aren't that far off. So there's not much there to tell you that, oh, I'm in the wrong mode. Sometimes they're like crazy off and you're like, how did I end up with a negative number? And it's obvious that something's wrong. And sometimes it just looks very, very similar. So be careful about your calculator's mode. If the question is in degrees, make sure you're in degree mode. If it's in radians, make sure you're in radian mode. But yeah, once we're comfortable that that's coming from the proper mode in the calculator, just as you said, multiply both sides by that 100. And 62.5 feet. How tall is that building? It's 62.5 feet. Fair. Well, that's just the tangent function. Why did we use tangent? Because we knew an adjacent and we wanted an opposite. Well, what if we're given different information? Here's the kind of classic kite problem. You have 100 feet of string out to a kite. And somebody comes up to you and asks you, hey, mister, or hey, ma'am, how high is that kite? Well, if you can find or approximate that angle, nowadays you all got phones, you put an app on your phone to calculate the angle. Look it up and cite to it, you'll find that angle. Let's say that angle is, let's say it's 28 degrees. We'll do one in radians in a minute. Can we find that height? Well, we can't find it using tangent.
We can find it using
Sine.
a hypotenuse one.
Since we know a hypotenuse, we'll want one of the
Yeah,
hypotenuse
sine.
ones.
I heard
And-
someone else say sine.
Yeah. Since we always think about which one do I want, which one do I know, and what pairing is that? We want the opposite. We know the hypotenuse. Well, sine talks about opposites and hypotenuse. Again, so does cosecant. But given the choice, we'll use our primary ones. So the sine of our angle, still in degrees, is that opposite length, h, in ratio to the hypotenuse, 100. And if we wanted an exact value, well, multiply both sides by that 100. 100 times sine of 28 degrees is actually a perfectly reasonable exact answer, if that's all we got. But we might as well find a decimal approximation for that since we've got the ability to do so. What is the sine of 28 degrees?
It is 0.469.
Multiply that by 100 and 46.9 feet. You guys happy with that so far?
Mhm.
And I guess for completeness, it might be nice to do a cosine example. Let's say, we know, let me do it that way. Let's say we know this angle is, what do I want? How about 1.1 radians? And we know this side length. Do we want to know that side length? Yeah, let's say we know this side length is 4, and we want to know that hypotenuse length. Now, that might look like a similar relationship as the one we just did with sine, but notice we know the other angle, right? In reference to this angle, that 4 isn't the opposite length, it's the adjacent length, right? Does that seem reasonable?
Shoot, dang, you're right.
So in reference to
So
that
we would
angle,
use,
that's the adjacent side. This is a hypotenuse. So we would use the cosine of the 1.1 equals 4 over that x.
And we put it in radian mode instead of
Yeah.
degree mode.
Yep.
Brain. Forgot the word.
So use that 1.1 radians and solve that for x. I want to make sure we're happy with that solving process. It's a little bit different when that it feels a little different when that x is in the denominator. So take a moment and solve that. So anytime we're trying to solve for a variable that's in a denominator, what do we do?
Multiply both sides by that denominator, or by that variable, I guess.
It's a great answer. And actually, by the whole denominator is often helpful. So I wouldn't criticize that at all. So x times the cosine of 1.1 would equal 4. Don't necessarily need those extra parentheses there, just like them. Then we can divide both sides by that cosine 1.1. And you could have done that with the decimal approximation you had there instead, but I find it easier to move the symbols around. So what'd you get when you took 4 and divided by that cosine of 1.1?
8.82 rounded.
8.82. Anybody want to back that up?
Mode, right? Yeah,
Yep,
okay.
that's what I got.
Yeah.
Okay. And that seems pretty reasonable in scale. 8.82. Questions about that? Now, I did purposefully, of course, move that angle up to being given this upper angle to reinforce the idea that our opposites and adjacents depend on what angle we're given. The kind of default of the opposite being the vertical and the adjacent being the horizontal, that's going to be kind of it's commonly going to be true because, if you recall from last time, we talked about when we measure our angles in standard position, we measure them up from a horizontal. So when we're talking about an angle in standard position, that opposite length we usually associate with the vertical, and the adjacent length we usually associate with the horizontal. But that is specific to being in standard position. Fair? So while that association is
Thank you for
common, be careful about where the angle you're talking about is, particularly later when we start getting into vectors. That's going to become an issue.
And this would work on the problems with the circle, right? Where you have to find a point along the circumference of a circle.
Almost. But I'll talk about that in a minute. Lots of stuff today. I'm not really a big fan of the 2 hours at a time. It's a lot all at once. I really
I mean,
prefer
hey
doing
man, if
hour
you
every
wanna
day.
if you wanna do lots of different classes in like 1 hour chunks, I'm okay with that. I can change my work schedule.
Yeah, but I can't do that to our schedule. I'd love to, but can't do that to everybody's schedule.
That's fair.
So as I said, though, that's our triangular definition. And the triangular definition is handy. A lot of the problems that we will be looking at and working with will fit nicely into this idea of angles in triangles. The problem with the definition this way is that it is very restrictive to only angles that fit in triangles. What if we have an angle that's, say, 400 degrees? You cannot fit a 400-degree angle inside a triangle. So we don't want to leave our definition that restricted. We want to open it up. But we want to open that definition up in a way that doesn't change our triangular definition, just expands it. So how are we going to do that? Well, we already looked at that in the picture I drew a couple minutes ago. If we consider an angle in standard position here, theta, then instead of having it be a triangle, if we consider this y value and this x value, then that x and y value are kind of like the opposite and adjacent legs of a right triangle. Fair? And if we knew the radius of our circle, r, then instead of defining these functions in terms of opposites, adjacents, and hypotenuse, we could define them in terms of our y value in ratio with our radius. And it's essentially the same function doing the same job. Define cosine as that ratio between the x and the r. We have our x as an adjacent and our hypotenuse as that radius r. What would that make tangent?
Which way did that go?
Opposite over adjacent would be y over x.
Yeah. Now, why is this definition different if it's all just changing those labels? Well, the thing that makes it different is, let's say we had an angle that went all the way into quadrant 3 there. So let's say that's, well, I don't know, say 4.1 radians. There is no way to have a triangle with that angle in it. But does that intersection point have an X value and a Y value? Yes, it does.
Yes.
Does this circle still have a radius?
Mhm.
Yes, it does. If
Where
we
would
knew-
you draw in the X and Y values in the third quadrant? Would you draw them facing up or facing down?
Oh,
Do you
You
know what I
mean-
mean?
I might know what you mean. I would tend to put them there, if that's what you mean.
Okay.
Was that what you meant?
Yeah, thank you.
You could technically draw them anywhere, but notice that drawing them that way gives us essentially a little triangle, right? Now, that triangle doesn't have the 4.1 radian angle in it, but it still has an opposite and it still has an adjacent and still has a hypotenuse in the kind of fake triangle. So our idea of the triangular definition still holds.
Would you be able to flip the triangle up so that you can use the, wait, never mind.
Yeah, no, I think I know where you're headed with that. And no, that starts to mess things up. But let's say we knew this point. Let's say this point was, let's see, negative 3.1. And that's going to make this angle different. It's negative 3.1 and, oh, negative 2.3. So let's say we knew that point in space. Could we figure out what the tangent of that angle phi is?
Would those coordinates give you the angle of that point in
They
the
could.
triangle?
They could. And will eventually. But if we just want to find that tangent value, well, the tangent value is supposed to be, well, it's supposed to be opposites and adjacents, but that's only in triangles. If we're out of a triangle, it's still those y's over x's. So that's just the negative 2.3 over negative 3.1, or 23/31. What if we wanted to know the sine of that angle, phi?
Well, we need the hypotenuse.
We need the, well, I'm going to say we need the radius,
Well, yeah, the radius, not the hypotenuse.
but you're right,
wording, same thing.
comparable to that. Absolutely. What would we use to find that radius?
Pythagorean theorem.
Okay, take a second and use Pythagorean theorem to find that radius. I'll give you a second to do that.
50.85, or just 8 if you want to round it to 1.
50 is way too large.
Yeah,
Yeah, it would be,
6.86.
wouldn't it? What did I
What's
do
that?
wrong?
Did you not square the end result?
I did not square the end result.
Or
Or
square root the end result.
square root.
$3.86.
$3.86 seems fairly reasonable. I mean, this is going to be like 9, and that's going to be like, I'm grossly approximating these. That's going to be like 6. So 15, square root of 15 is like almost 4. I mean, that seems reasonable. So if that radius is 3.86, then our sign would be negative 2.3, our y value, divided by 3.86.
I don't know what I'm doing wrong. I got 7.13.
Yeah, I was wondering, did you say
Oh,
15?
I'm still in
or-
radians. I'm still in radians.
Well,
No, that
that
wouldn't
shouldn't
make
matter.
it.
We're not. That shouldn't matter.
Never
We're
mind.
not.
I don't know what I'm doing wrong.
What'd you get when you squared the 3.1 and the 2.3?
50.84.
Yeah,
And
that's way
then
too large.
I square rooted the answer and I'm getting 7.13.
Yeah, but that's way too large. I mean, 3.1 squared is less than 10, I think, and 2.3 squared is less than 8. So there's no way that adds to 50.
Did I put the wrong symbol there?
Did you add them
Line?
together and then square them?
I accidentally multiplied and I did
Ah, that would do
a
it.
squared times. Yeah.
That would do it. It had to be something.
Mhm.
All right. Now, this is our most general definition for our
There it is.
trigonometric functions. And of course, the cosecant, secant, and cotangent, while we will often think of them simply as the reciprocals of their corresponding functions, they too fit in this definition. This is our most general definition for our circular trigonometric functions. But there is actually a modified version of this definition that we will tend to use somewhat more often. And that's to take this circle and make it a particular size. So, for example, if we had this radius 3.86 circle, there's always going to be a circle in here somewhere of radius 1, right? I could always draw
Yes.
that circle of radius 1. And that circle of radius 1 is also going to have a point on it. And we could define our trig functions based on that point on that circle. So
But wouldn't that point be the same as the point on the bigger circle?
would it be wouldn't be the same, but it would be the same in ratio. This point wouldn't go all the way out to 3 and 2. 3 is there, down 2. But however far it goes out and down would have to be in the same ratio as that 3.1 and 2.3. Does that make sense?
Yeah.
So the values are going to be different, but the ratios are all going to be the same. So it's often going to be handy for us to, instead of forcing ourselves to be on a circle of whatever radius, the problem happens to want us to be in, to be in a circle, force it to be a circle of radius 1. So if we imagine a point on that circle of radius 1, I'm going to give you a point on that circle here, negative 3/5 and 4/5. Again, you can use Pythagorean theorem to make sure, to test and make sure that point is on a circle of radius 1. Make sure Pythagorean theorem puts out that 1. It will. The nice thing about defining it on the unit circle is if you're defined on a circle of radius 1, your sine value, instead of being the y value over the radius, since the radius is 1, it's just that y value.
How?
Well, the radius is 1, right? So instead of being y over some arbitrary radius, it's y over our specific radius of 1. And y over 1 is the same as y.
Okay.
What would that make the cosine?
X.
Yeah. The tangent?
Make it 1.
Only in specific cases. It's still the y over x. There's no r in it, right? So the fact that we've specified the radius as 1, that's the one where it doesn't matter. Fair? So for this particular point, the sine is just the y value, 4/5. The cosine is just the x value, 3/5. The tangent, okay, that one we have to do some work with, but it's just the 4/5 divided by the negative 3/5, which is going to reduce to negative 4/3. So when we can be on a circle of radius 1, we get kind of simplified definitions, which is going to be handy since we're going to be able to force ourselves on a circle of radius 1 surprisingly often. So I want you to start kind of associating those with each other. Associate your sine value with your y's, your cosines with your x's, your tangents with that ratio between y and x. Questions about that? Well, if all of this is supposed to be handy, would it be nice to know some points on that circle at important angles? I think it would be nice to know some points on that circle at particular angles. Well, maybe there are some handy angles that we could figure out those points for. You brought up standard angles a while ago. The reason those angles are our standard angles is because we can geometrically figure out what those coordinates are on the unit circle for those angles and any multiple of those angles using a couple of geometric arguments. And I want to go through those arguments now. So let's take this pi over 4 angle, or same as a 45-degree angle. If you've got a 45-degree right triangle, then that would be 45 degrees. This would have to be 45 degrees because they all have to add up to 180, right? if we choose to make that hypotenuse 1, why a 1? So it fits in our unit circle here. We can try to calculate the other sides based on that length and those angles. So if we just arbitrarily label this side length A, what do we know about that other side length based on our 45 degrees?
It's the same as A. They're both equal.
Yeah, because those angles are equal, those side lengths have to be equal. So it's an isosceles triangle. So when we put that into the Pythagorean theorem, we only have one unknown, that A value. So we can actually just solve this. A squared is equal to 1/2. So A is equal to the square root plus or minus of 1/2. Now you wouldn't leave the square root of 1/2 like that. Square root of 1 is 1, square root of 2 is just square root of 2. And you would even go so far as to rationalize that, right? Right? Because you're nice and polite. So in our triangle, these side lengths turn out to just be a nice square root of 2/2. A nice solvable value. So what does that make this coordinate on our unit circle? Well, that coordinate is the square root of 2/2. Square root of 2/2. Is that fair? Similarly, what if we went over here to 3π/4? Does this same triangle fit right here? So what do we know about those x values and those y values?
X values are negative, but they're still √2/2 is just negative √2/2.
Well,
And then
and
y
remember-
values is a positive.
Remember down here that a was technically plus or minus square root 2/2?
Would it be the same?
The same except for the signs. Except that you've got that negative for the x and that positive for the y. You might have just disregarded that plus or minus because we're in a triangle, but we're not necessarily in a triangle, right? So that positive or negative starts to have a nice meaning. What about down here at 5π/4?
They'd both be negative values.
But the same lengths, right? It's still negative square root of 2/2. Negative square root of 2/2. Down here at 7π/4.
It would be positive, negative.
Right. Positive, negative. So if somebody comes around and asks you, what is the cosine of 7π/4? You're going to tell them, well, cosine is the x value on the unit circle. At 7π/4, the x value on the unit circle is a square root of 2/2. So that's the cosine of 7π/4 radians. If somebody asks you what's the, I don't want to use cosine again. Somebody asked you what the sine of negative 3π/4 was. Well, negative 3π/4 isn't on our diagram, but negative 3π/4 is coterminal. 1, 2, 3 is coterminal to 5π/4, right? So the
then
coordinates
it would
have to be
just
the same.
Negative, negative.
Well, the point would be negative, negative, but with the sine function, we want the y value, right?
Yes.
So we would grab that y values, negative square root 2 over 2. So with just this, not only those standard angles do we know the trigonometric values for, but for any multiple of pi over 4, we know the cosine, sine, tangent, cotangent, cosecant. We can find all of them. Cool. Okay, well, that's the over 4s. What about the over 6s and over 3s? Would it be nice if we could make a similar geometric argument for those? I'm assuming you all say yes. That would be fabulous. Right? That would be fabulous.
As long as you're going to test us on it, then yes, that would be fabulous.
Do you want tests?
You want to learn more than just test stuff, right? And
Ideally,
yes,
yes,
it'll be on
but
every
realistically, I want to know what I'm going to be tested on too.
It'll be fabulous. So the nice thing about the pi over 3 and the pi over 6 is they actually both exist in the same triangle. Because pi over 6 plus pi over 3 is pi over 2. The 30 plus the 60 is 90, right?
You're a crazy man.
I know. So that's nice. We don't need a separate triangle for pi over 6 and for pi over 3. We all get it in one. We're still going to make this hypotenuse length 1. You'll notice if you've been reading your textbook, please be reading your textbook, that your textbook actually uses a 2 for the hypotenuse in both of those for some silly reason. I hate when they do that. You let it be a 1 so it fits in that unit circle. Now, unfortunately, like the 45-degree triangles or the pi over 4 triangle, those side lengths aren't the same. So we can't use the same trick. But if we mirror that triangle over here, this is pi over 3, that's pi over 6. What do you notice about this big triangle?
It's equilateral. All sides are the same.
Yeah, that's a 30 and a 30, so that's a 60. So it's 60, 60, and 60, or pi over 6 and pi over 6 makes pi over 3.
So
So-
then all the sides would be 1.
So all the sides are 1. Which makes this little pink side here, because they're
Half?
mirrored, it's exactly 1/2. Now that doesn't tell us what this other side length is, but since we have 2 of them, Pythagorean theorem would certainly let us know that third, right? So just real quick, 1/2 squared plus b squared is equal to 1 squared. So 1/4 plus b squared is equal to 1. Subtract the 1/4 from both sides. So b squared equals 3/4. So b is equal to plus or minus that thing's square root. Square root of 3 over the square root of 4 is 2. So in our triangle, we'll just use that square root of 3 over 2. But in our circle, some of them will be positive and some of them will be negative. So it's a neat little trick, the reflection trick for the 30-60 triangle. But it does allow us to then know what these coordinates are. The pi over 3, for example, over 1/2 and up square root of 3 over 2. So 1/2 and square root of 3 over 2. The pi over 6 is the same triangle. It's just laid down instead. So the longer side is now the x, the square root of 3 over 2, and the shorter side is the y, the 1/2. You better believe we can extend that all the way around this circle. That line's going to bug me if I leave it. So could we fill out the coordinates for all of those points all the way around?
We'd just be flipping it, and then depending on what quadrant it's in, negative, positive, negative, negative, positive, negative, or positive, positive.
And like we talked about at the beginning, at first it seems like a tremendous amount, like an overwhelming amount of information on this little diagram. Like, how am I supposed to know all of this stuff? Well, there's only a couple of numbers here. 1/2 square root of 2 over 2 and square root of 3 over 2. They're just flipped around. So it's all about, well, why is it positive or negative? Well, we know what quadrant it's in. The positive and negativeness comes from which quadrant we're in. How do we know where the square root of 3 over 2 and the 1/2 are? Square root of 3 over 2 is longer. So is your x longer or your y longer? You know? So we don't have to kind of memorize all this information. If we know those two triangles and know where our radian measures are, we can build this tool fairly nicely. When I'm doing in-class classes on the second or third Monday, so it would be this coming Monday, one of the things I would often do is give a quiz, and the quiz is, here's a blank circle. Fill it in. And students would fill in the radian measures in one rotation, building it like we've talked about, and they'd fill in those coordinates all the way around. And it does at first seem like a daunting amount of information, but once you mess with it for a while, it does start to seem much more reasonable. So I recommend, I'm not going to have you guys do that because I don't have you guys in class where I can give you quizzes and whatnot. But I do recommend spend some time and build this thing. Draw it out, label it all out, construct those angles. Heck, get some construction paper and cut out some little triangles that fit and see yourself flip those triangles around and form all those measurements. The more kind of muscle memory you can give yourself for where all these things are, the faster you will get comfortable with this tool. Fair?
Fair.
So now if somebody walks up to you and says, hey, what is the sine of 7 pi over 6? If we know this tool, we can tell them. If they ask, what is the cosine of negative 5 pi over 3? We can tell them. And tell them exactly. If they ask, what is the tangent of 13 pi over 6? And yeah, I am kind of asking you these. What is the sine of pi over 2? What is the secant of What do I want there? How about negative 4 pi over 3? We should be able to use those definitions and this circle diagram to answer all of those. Take a minute and do that, please.
Damn it.
Okay, so what's the sign of 7 pi over 6?
Negative root 2 over 2.
Well, 7 pi over 6 is down here. Sign is which? The x's or the y's?
It is the y.
So the y value would be the shorter one. So it's going to be the negative 1/2. Right place. Careful about which coordinate. Cosine of negative 5 pi over 3.
Positive 1/2, if I'm thinking about it right.
So what quadrant is that in?
1.
Negative 5 pi over 3.
I think it is almost all the way around. I think it's in quadrant 1.
So
If I
1,
thought about it
2,
right.
3, 4, 5. So it's over here. It's coterminal to pi over 3, right? So it's the same, lands in the same place as the pi over 3 does. Cosine is the x value. In that quadrant, cosine is positive. So, because the x values are positive. So yeah, positive 1/2. Little bit harder. Tangents are always a little bit harder. Tangent of 13 pi over 6. What quadrant is that in?
Quadrant 1.
It is in quadrant 1. 12 pi over 6 is 1 rotation. So 13 pi over 6 is 1 more. So we are coterminal to pi over 6. So we're right here. Tangent in quadrant 1. Since both coordinates are positive, the tangent's going to be positive. Tangent is positive in quadrants 1 and in quadrant 3, where they're both negative. Sine is positive in quadrants 1 and 2. Cosine is positive in quadrants 1 and 4. It's good to know that. But tangent is supposed to be our y over our x. So our 1/2 over our square root of 3 over 2. But you wouldn't leave it like that, right? You wouldn't leave it like that. And you wouldn't get a decimal approximation, right? Point of these is we want to try to stay exact. So that's 1 over the square root of 3. Leaving it like that would be a little bit rude because leaving people radicals in the denominators is just rude. So let's clean that up.
So root 3 over 3 is the same as root 2 over 2.
No. Root 2 over 2.
Oh, sorry, I was misreading your writing on the.
Oh, okay. Oh, on there? Okay, yeah.
Yeah,
Yeah. Got a little squished. There's a lot on that diagram.
there is. I tried to make my own and it is not pretty.
I made my circle way too small when I tried to draw this out.
Oh, yeah. It's good, big as possible.
Big as possible.
And really do draw it out and build it out a couple of times. You do it, even 5, 6, 7 times, it just becomes part of your brain after a while. What about the sine of pi over 2?
I just got 1.
How'd you get 1?
Yeah,
I put it in my calculator.
Aw, the whole point of this tool is not to need that, right?
Well, I couldn't figure it out
Is
in my
it-
own brain.
Got 0.
there is no x. It's just the y, and it's on a unit circle, and the unit is 1. So that point is at 1.
I like 80% of that.
What
Damn
was
it,
the
what was the
20% that
20?
you didn't like?
You said there wasn't an x coordinate,
Well, the x is 0. Sorry.
which is a perfectly valid, perfectly reasonable x coordinate. Fair?
It's hard to
Fair.
switch from 0 is nothing to 0 is actually important.
Well, make that switch right now.
No, it's like everyday life, 0. Oh, there's nothing there.
So the sine is the y value. So yeah, it's 1. If we asked what the cosine of pi over 2 is, what's the cosine of pi over 2?
It would be 0.
It'd be 0. What about the tangent of pi over 2?
That's a great question.
That would be broken calculators.
Is that something that you can do?
Well, that would be 1 over 0, right? Which is,
Something.
it's undefined.
It's gotta be something.
It doesn't actually. Remember, we can't divide by 0, right?
Yeah.
And don't even say that's nothing. The word nothing is very dangerous in mathematics anyway.
No, this is just confusing. It's something, it's just confusing.
So yeah, any of the trig functions that have division in them, they all kind of do, but when you're dividing by the radius, your radius is never a 0, so that's safe. But tangent, cotangent, secant, and cosecant all divide by either x or y. So each one of them will be 0 in the denominator from time to time. So each of them have the risk of being undefined sometimes. Sine and cosine are never undefined. The others have places in the rotation where they're just not defined. And we'll talk when we talk about how to make graphs of these. We'll talk about some real life physical interpretation of what does it mean physically when we're turning something to have this undefined point in it. And you'll find that it actually does have some real solid meanings. If you'd like a preview of that, if you are standing off of a railroad watching the train go by, right? So you're watching the train zip by. As you watch the train zip by, your head rotates, right? And how far the train is away from you is related to that angle, right? Is that fair?
Mm-hmm.
So how far away is the train when that angle is, if this is 0, how far away is that train when that angle is 90 degrees?
Long.
That's undefined, isn't it?
That's
It's
undefined.
not you're not even looking at it at that point. You're looking past it.
Yeah. You're looking parallel to the track. You're not looking at the track anymore, right? Anything less, even like 89.999, you're going to see the train way down there somewhere. At 90 degrees, no train.
That's tunnel vision.
That's tangent. You set me up for that. I appreciate it.
You're welcome.
So there are real physical interpretations of these undefined locations. Like, well, why should there be something undefined? Because there are things that you can't look at. Anyway, secant. I don't like secant. I like cosine. So let's say we asked what the cosine was instead. What's the cosine at negative 4 pi over 3?
It's -1/2.
Would be negative 1/2. Well, what does that tell us about what the secant is?
Would the secant have to be -2/1?
Yep. It's reciprocal.
Neat.
Yeah. So back to your question from like an hour and a half ago, what makes these standard angles standard? What makes them significant? What makes them significant is we can find geometrically these values, and we can find them exactly. So one of the ways that you use this in practice is, let's say, for example, you're trying to figure out how far it is, across that proverbial, river. How far is it across there? So you can build your bridge or whatever. So you want to know how far across that river is. And you only have fairly rudimentary tools. You can walk out this distance until that angle reaches an angle you know about. So let's say we walk out until that angle is 60 degrees. Well, how are we going to know that angle is 60 degrees? Do you go camping with an angle finder? You should. It's fun.
You don't know my life.
Even I don't go camping with an angle finder. You build them. You want the thing to find 60-degree angles? Take 3 sticks, make them the same length, and then form them into an equilateral triangle. Each of those angles are 60 degrees, and you can sight 60 degrees with that. Fair? So walk out until you find your 60 degrees. Count your steps. Say this was 12 paces. That's very far. It's a big river. That's 12 paces. Well, how far across is the river?
It's
Well,
equilateral, 12 paces.
it's not equilateral.
Oh, no, sorry, brain.
That would be, and this long length would be 24, right?
Mhm.
But that still doesn't tell us what this length is. So we would know that's 24 because of the equilateral reflection we could make, but that still doesn't tell us what this length is. But we do know that the tangent of that 60 degrees has to be equal to this opposite length. I'm going to call D for distance, over our adjacent length, 12. So 12 times the tangent, if we multiply both sides by 12, 12 times the tangent of 60 degrees has to be that distance. But how are we going to find the tangent of 12 degrees? Oh, sorry, the tangent of 60 degrees. Well, we know it already. It's up here. The tangent of 60 degrees is the same as pi over 3 radians. So I'm going to write it. I don't like that orange. If any of these colors are hard to see on the black, by the way, let me know. So the tangent of 60 degrees, the same as that pi over 3, is going to be that square root of 3 over 2 over 1/2. Multiply those by 2, and you get the square root of 3 over 1, or square root of 3. So tangent of 60 degrees, square root of 3. So that's an exact value for that distance. Now, we're not always going to be able to find exactly the angle that we want. So when we can build 30s, 45s, and 60s, then great, we can use these nice exact values. But there's a problem with that. What if you need, say, 15 degrees or 22.5 degrees or something else? There is a way to build, and we'll talk about it a little bit, a way to build any other angle you need by adding, subtracting, halving, doubling these standard angles to build the angle that you need. And we will look at some of those tools, how to find the sine of of the subtraction of two angles, or half of an angle, or double an angle. We will learn some of those tools. We will learn it more for its algebraic manipulation properties. But in the old days, you would use those tools to find whatever angle you needed based on these three angles. Just by, again, adding, subtracting, multiplying, dividing those angles together to get what you need. Nowadays, we don't have to do that. Nowadays, if you have any particular value, let's say, 115 degrees. I don't know why I'm back in degrees. Oh yeah, I know why I'm back in degrees. That's why I'm back in degrees. And you want that point out there on a circle of, let's stay with radius 1 for right now. And we wanted those coordinates. We don't have to do a lot of work to find that. All we need is our shiny box and some batteries. How would we find what this X value is?
We would do cosine.
Yeah. That's going to be the cosine of 115 degrees. And the Y value?
Be sine of 115 degrees.
Yeah. What is the cosine of 115 degrees?
0.9.
I got 0.42. I'm in degree mode, or negative 0.42.
Negative 0.42. It's got to be negative, right?
Hmm.
And at 115 degrees, I believe that more than the 0.9. The 0.9, you were probably still in radians.
I got 0.9 for sine, so that's probably what he did.
Oh, okay. That would also make sense. Sine would be reasonable upon 0.9. Anybody want to back up those numbers?
Yeah, I also got sine as 0.9.
Okay. Now, the disadvantage of that calculator, doing it that way, is we have decimal approximations and not exact values.
Yes.
And it might not seem like that big of a deal. We use decimal approximations for a lot of things in the modern world. But just to kind of put it in a little bit of perspective, if your angle is off by, say, some little tiny bit, say it's supposed to be there, but it's just a little bit different. It's only off by like 0.01 degrees even. Well, like how much difference is that going to make in, you know, your final answer for something? Depends on how far out you go, right? If this angle is really small, if the error is really small over, 5 or 10 feet, it's not that big of a deal. But if you've got a 3-mile long bridge and you're off by 1/100th of a degree, that's several feet on the other side of that bridge. Fair? Let alone if you're trying to have your satellite hit a certain location or your Mars lander hit something. In angles, those little errors can make a surprising amount of difference. So we really want to be able to work in exact values when we can. Hence, some of those exact value tools still being very useful. But as long as we carry a fair amount of decimals, this 0.9 made me a little nervous, but as long as we carry a fair amount of decimals, we'll generally be okay. But it's nice to be able to work in exact values when possible. Fair?
If we had that angle in radians, would it be easier to find the exact value?
Not necessarily, not really. I would say yes, because it turns into a lot of work with fractions as opposed to decimals, and I like decimal fractions better than decimals. But mechanically, not really. They're both a pain in the butt. We'll talk about how a little bit about historically how that's done later. But really nowadays, if you need to do it, you do it with some tools from calculus. They're just so
Okay.
much faster, so much faster. You know, those tools, the angle sum and difference tools, the half angle formula tools, they're still very useful, as I said, for their manipulation power, but not so much to actually find angles anymore, because the calculus tools are so much more powerful. So, interesting kind of question here. The sine of that 115 degrees, we decided was 0.9 something, right?
Is 0.9063 carrying.
I just feel better about that.
That's
So find another angle in the first rotation, so between 0 and 360 degrees, such that the sine of that angle is the same.
Just looking for coterminals again.
Actually, no,
No?
because coterminals would have to be outside of the first rotation.
Wouldn't it be 25 degrees?
Why 25 degrees?
Because it's the same height and sine is the y value, and so if it's you go back the 90-degree angle to the same angle over there, and then 115 minus 90 is 25.
So you're saying this angle is 25, right?
Yeah,
That means you want this angle to be 25, which means this angle would be what?
25.
65.
65. Because those have to add up to 90. I think the better thing to have done, instead of subtracting the 115 from the 90, subtract the 115 from 180. This angle is the other 65 degrees. So this one has to be 65 degrees. Fair? You're certainly correct that this angle is 25 degrees. So this angle has to be 25 degrees. But angle in standard position that's giving us that ray with the same height is that 65 degrees. Does that make sense as an important distinction? Who had said the 25? I didn't catch it.
I did, and I'm still very confused now.
Well, you said it had to have the same height, right?
Yeah.
So, oh, that red is very aggressive. I don't mean it to be aggressive. So at 115 degrees, measured from standard position, that had a particular height, and that height was your 0.9, right? And you very accurately said, well, we just have to be somewhere where it has that same height value, because that height value is our sine, right?
Yeah.
So you wanted to figure out what this angle, whoops, change that color. You wanted to find out what this angle was, right?
Yeah.
All of that, I'm 100% with. But then what you said was you subtracted the 115 from 90, right?
I subtracted 90 from 150.
Or 90 from 115, right? That gave you this angle, right?
Yeah.
This angle is the same as that angle, right?
Yeah.
So this being 25 degrees means that's 25 degrees. But we didn't want that yellow angle. We want that pink angle. Fair?
Yeah.
But could you not subtract 25 from 90 then to get the rest of that angle?
You absolutely could. Subtract 25 from 90, and that's your 65 degrees. Fair?
How else could you have found the 65?
What's that?
How else could you have found the 65?
Well, probably the more straightforward way. And there's nothing wrong with finding it that way. If that's what you see, go for it, you know? Oh, that's a terrible circle. That's why I use my circle thing. But what tends to be easier is to measure all of our angles from the x-axis and don't measure them from the y-axis. You'll notice almost all of our tools will be measuring from the x-axis, not the y. Just tends to be nicer for us. So that 115, subtract the 115 from 180 instead, and that gives you that this angle is 65 degrees, And then that mirrors over to the 65 that we want. Is that better?
Yeah, that makes more sense.
Okay. So at 65 degrees, both the sine of 115 and the sine of 65 degrees is both the same 0.9063 equals the 0.9063. What if we want to find an angle? Actually, I'm just going to change that. I'll rewrite all that. Find another angle theta such that the cosine of theta is equal to that negative 0.42. Now, even before we try to do that, what quadrant would that have to be in?
3?
It would have to be in quadrant 1, right?
No, it needs to be negative.
Oh, then it
Needs
would
to
be in quadrant 3.
So quadrant 3, right. Cosine is negative where our x's are negatives. X's are negatives in quadrants 2 and 3. We are given the 115s in quadrant 2. So the answer that we're looking for had better be down here in quadrant 3. Where the horizontal distance is the same. Well, if that horizontal distance has to be the same, do we know what this yellow angle is?
That's 65 again.
Yeah, it still has to be 65.
Right.
Or if you prefer, what about this red angle or orange angle? Do we know what that orange angle is?
115.
Perfect. It's 115 degrees. So we could either add the 65 to 180 or subtract the 115 from 360. Either way, we should get the same result.
245.
Plus the 65 degrees. You said 245.
Mhm.
I'll buy that. So the cosine of 245 degrees is equal to negative 0.42. 2. Oh, man. Does that seem reasonable? Now, I bring this up for 2 reasons. One, you've got some questions on your homework for 5.3 that essentially ask the same question. Find another angle that has the same sine value or the same cosine value. We don't actually care what those values are, but find another angle that has the same sine value as 115. Well, we did that. That was
You
our
have to
65.
start all the way from 0, right?
Yes,
For
when
those
measured
homework
from
problems?
standard position.
Yeah.
But not only that, later on, when we start using our trig functions backwards, and this gets back to something you said, once we start using our values to start generating angles, we're going to have to be careful about this because we're going to get answers in multiple quadrants. So we're going to get like one answer of 115 and need to consider the other possibility of the 65. So this question of what other quadrants or what other locations does this same value come up is going to be important. So for example, if I had said what angle makes sine into 0.9063, I think it was. Well, how many angles are going to have that value? Well, anything coterminal to 65 and anything coterminal to 115. That's a lot of different angles, right?
Couldn't it only be the 2 since it's positive?
And anything coterminal to it. So technically, what, 360 plus 65. So what, 425 degrees.
Okay, I see what you mean now. Okay.
But you're right that it's only the 2 in any particular rotation. Fair? So we'll need to find the 2 in the first rotation and then say, and everything coterminal to this. So this idea of every trig value, every ratio value happens in 2 spots per rotation. That idea is going to be really important later. So these questions about, I mean, they seem like kind of weird questions, find another value such that questions, like why do we care? That's going to be a big deal later. Fair? So give some attention to those problems. Okay, was this helpful today?
Yes, I think I better understand the 5.2 and 5.3 homework now. I already did them and turned them in. I just didn't really understand a whole lot of it.
And as I mentioned, be gentle with yourself about this stuff. It's a lot of information that kind of, it doesn't all make sense until it all makes sense at the same time. So what you're looking for is this kind of all to be crazy. And then after a while, it'll kind of, everything will start linking up and you'll start seeing the connections and you'll go, okay, this is meshing together. Let that happen over time. One of the things I want to ask you guys to do, because we only meet twice a week, and we have a couple of days like this week, us missing Monday for Martin Luther King. It's an important holiday, don't get me wrong, but us losing one day and one of our 2 days a week is a big loss. So one of the things I want you guys to think about sending me is requests for specific video information. Like, can you make a video on this thing, or can you make a video on this thing? So I can make those and send those out to you, particularly between Wednesday and Monday. That's a long time. Fair? So let me know what I can make. Let me know what you guys need, and I'll send those out. Okay?
Oh yeah, by the way,
I
the
had this
discussion
too.
boards are locked.
Why are the discussion boards locked?
The dates are set to
The
2019.
due dates are for 2019.
Oh, of course they are. I will go fix that. Thank you.
Post anything.
I was wondering why no one was posting anything.
Yeah. I thought you guys were just shy.
No,
Okay.
we were just locked out of the forums.
Yep. Thank you for mentioning that. I'll go fix that. Cool. Okay. Then I'll hope to hear from you guys soon. And if not, I'll see you on Monday.
I had a question
Alrighty.
about homework.
What was that?
So is all of the homework getting pushed back?
Yes.
Or
Yeah.
you're
I'm going to
something
scale all those back.
Besides 5.3 due on Sunday.
On Sunday, let me look at the calendar.
I think it's 5-4.
Oh, yeah. Yeah. Those didn't get pushed back. From Monday, we're about a day behind. So I think, let me just do this. Let me move the 5-3 to Sunday and then move those others back out. So we have some time to talk about 5-4 and 5-5.
Okay.
Cool.
All
And
right.
I will do that right now, because if I don't do it right now, I will forget, because I am like that.
Same.
I get it, dude. I'm
Yeah.
the same. If I don't do it right then, I will forget it. And then it's never going to be done.
That's a good tip for me. If I say, oh, I'm going to send you something and you don't see it after a while, kind of go, Matt, where did that end up? Because sometimes I put it in the wrong place. And sometimes, so I respond well to nagging. That's what I'm trying to say. So,
Okay, speaking on that, like, if I remember right, you said that My Open Math was the best way to contact you.
yes.
Okay, what do we do if it says you haven't read it yet? Do we just like message you again?
Yes. Because
Okay.
that means I had some problems with, one of the reasons your screen is, the web thing is black right now. My other computer just gave out.
Ah,
So I had to rebuild my entire system now. I like the black. It's easier on my eyes. I don't know if it matters for you guys, but
Oh, I
It's
like that a
easier
lot
on
more.
my eyes
Oh,
too.
good.
Everything that has the option of dark mode is in dark mode. for
in
me.
dark mode.
Yeah.
But yeah, I
Yeah.
spent the weekend rebuilding computer. So
Isn't Discord defaulted to dark mode now?
Yeah, I think so.
so that should get better, hopefully. But yes, in general, if you send me something, oftentimes I'll like look at it, read it, go, oh, I'll make myself a note, and then stuff gets, So nag. I love nagging.
okay, you answered it in class today, so it's like
Awesome.
fine now.
Good. And speaking of which, let me not forget to move this because I started talking about stuff. I said I was going to move 5/3 to Sunday and move the others out. And I'll populate those dates out as we go along. I'm happy to give you guys time to work on stuff as long as you guys are working on stuff, The dangerous thing is people getting behind, and I don't want that to happen because that can get kind of messy in this class. But I do want you to have time to work. So be working and we won't have a problem with stuff being pushed out. That all sound good?
Yep.
Yeah.
Okay. Cool. Anything else you guys need?
I think I'm good.
Okay. Then have a wonderful rest of your evening.
Have
And
a
I'll see you
wonderful
guys
night.
later. Thank you.
Thank you.
Take care.